Good morning to
Good
one and
morning.
all.
Huh?
Yeah, we are here. Dr. Deepa Srinivasan. She was presently working as a eminent professor and as well as dean at Ramaya University, Bangalore. And prior to joining this Ramaya University, she was working as a chief engineer and Pratt and Whitney and R&D center at Bangalore. And she also having almost 25 years of experience in the area of gas turbine materials and leading research development, high performance temperature materials and manufacturing technologies for gas turbine engines from Pratt and Whitney and as well as from GE. And she is also having more than 35 patents, and she has developed more than 50 technologies transferred to the gas turbine and steam turbines and all. And she is having a vast experience in the area of metal additive manufacturing and has developed several applications for the metal additive manufacturing for gas turbine applications and as well as for the healthcare implants via this additive manufacturing process. And she is also a ASM international member, and she is a fellow of Indian National Academy of Engineers and as well as distributing alumnus of the Indian Institute of Science and Women Engineer of 2020. INA has several Engineers Excellence Awards from General Electric and as well as Pratt& and Whitney. With this short brief introduction, I will now welcome you, Dr. Manam. Over
Yeah.
to you.
Yeah. Thank you so much. Are you able to see my screen?
Yes, Manam, I can able to see you.
Sure. So, good morning, everybody. And first of all, thanks for the opportunity to NIT Warangal, to Professor Venugopal and Dr. Manjaya for inviting me for this yarn course on applications related to additive manufacturing and repair. And of course, Professor Shrikant Joshi from University West, Sweden, for introducing me to these colleagues. So, what I'm going to do is to share some of the published work. But this is dated during the time I was in GE, but it's all in published literature. And going to give you a brief overview on how there are some of the challenges while taking qualifications, while taking additive manufacturing for qualifications of very high-end structural engineering applications, such as in a gas turbine or it could be in any sector. And but long before today, additive is a buzzword, but long before that, we were able to showcase some of the early work in terms of qualifying both using laser powder bed fusion as well as direct energy deposition. That's what I'm showing on the left hand side and the right hand side. And the middle is, I'll share a glimpse of what some of the published work and related to cold spray technologies, which is being treated as an additive manufacturing technology, though it comes in the category of thermal spray and cold spray. I just wanted to check, are you able to see my mouse? Uh, are you able to see me moving the mouse?
Yes, yes.
Or maybe I'll use the laser pointer. Okay, so I think in the last 4 5 days you would have heard a lot of very good introduction as well as several details of the historical evolution of different types of metal additive manufacturing as well as polymer based additive manufacturing as well as more recently designed for additive manufacturing. I won't repeat any of those. What I will just show via this chart is basically y-axis is simply showing the complexity of the part and the x-axis is showing what are the different process related parameters, just to give you a process map of which additive manufacturing technology is the right one, form fit and function to choose for each application. So even if you're in the academia and you would like to look at fundamental aspects of these, it is always good to keep in mind at least the end application, and then look at the research aspects. What are the challenges in those research aspects? For example, if it is a very very large part, it is not very feasible both economically as well as process wise by using laser powder bed fusion. But it's a part, very very small part, such as what Mr. Santosh would have told yesterday, in design for additive manufacturing with very high resolutions, then it may not be feasible or viable to go with direct energy deposition, because then you can't get the kind of finish, surface finish, and the part resolution, and it needs extensive post processing. So based on the simplicity and the complexity of the part and based on the throughput, high versus low, that means how many parts do you need. For example, if you're in the automotive industry, many tens of thousands of parts every day. Now if that is the case, then which is the technique to use. So before starting the research or something, it is good to keep this in mind. So I thought I'll just showcase that and start off on repair applications. So one of the things is, this is a very old chart taken from the literature, and then this just gives, it's also not very updated. You can see it's tracking about 70-75 years of historical evolution of various type of gas turbine materials, especially for the turbine blades. As many of you know, in any structural engineering turbo machinery, especially in something as complex as gas turbine, in this context we'll be talking about both industrial gas turbine as well as aero engines. Then you can see here that, typically it takes a lot of effort to be able to get a very small percentage of efficiency. You can see that 40% to 60%, it has almost taken 1970 to about 2005, almost 50 years it has taken. 40% in 40 years means 1% every calendar year. Similarly, on the y axis, this y axis, if you look at the firing temperature, in going from 1000 degrees to 1500 degrees, again, it is basically 500 degrees. It has taken about 50 years, let us say. So, we are talking about very, very small, very, very complex machinery and very, very complex. You know Design criteria. So this is reaching a natural asymptote. So that is where, for example, additive manufacturing comes to the rescue, because you don't have structural engineering materials in the periodic table that can that you can randomly use. There's only so much available, and there's only so much alloying, so much manufacturing you can do. So I wanted to share, I think it's not there here, but I wanted to share what is called typically a plot of weldability, or a plot of alloy content versus different alloys that are used in a turbine blade or a turbine vane. Where manufacturing process, what you can see in the bottom is equiaxed to directionally solidified to single crystal, and alloy development are the processing are the main enabler of gas turbine efficiency, as it is written here. So it boils down to the fact that how intelligently we are able to pick newer manufacturing technologies, combining with the existing materials that are already available, and trying to upgrade them to something like better performance, lower cost, and in shorter span for whichever application. Since I worked in the gas turbine industry, the application I'm showing you is for gas turbine repair and refurbishments. So again, on this slide, some of these names you're seeing here: Udimet 700, Inconel 738. This is a particular alloy which is single crystal N5, it is called. So some of these alloys almost defy the imagination of the designer, because these are nickel based super alloys, which are the main claim to fame to the gas turbine, the technology evolution. And they have so many alloying additions. Each of them plays an indispensable role. So when it comes to, the distress, when it comes to after service exposure, for example, in a gas turbine stage one blade, then the temperature decreases from top to bottom, and the stresses increase from top to bottom. It's a rotating process. So what happens? There is distress. Obviously, anything that undergoes service will undergo wear, rub, high temperature creep, time dependent inelastic strain, fatigue. There'll be holes, there'll be oxidation, there'll be metal loss. So many distress, or so many degradations will be there. And what I'm trying to say is we need to find newer solutions, because some of these are impossible to repair and refurbish. So where metal addition, in terms of metal additive manufacturing, and thermal spray coatings, where both these come into the picture as a savior. And this is something we started actually working on in long back, 15 years ago, as trials, as research and development efforts, and where we, long before additive manufacturing actually became a buzzword. And so, you know, those are the examples I'm going to be sharing with you, in the next hour or so. So, if you look at laser metal addition, then what are the key parameters for it? Basically, if you look at a new part, the tie line out here, and the this is the x-axis actually goes to the number of hours that it is going to be, hours or years that any part is going to see in service. Then if something on the y-axis at this level is the acceptance standards for qualification in the new make, then what happens is after every time it comes for inspection and repair, this is the first repair, second repair, and third repair, we are always trying to find out new technologies to be able to repair and send the part back without any damage for safe operating condition. Of course, when it is physically damaged, there is no question of repairing. And there is also the upper spec limit and the lower spec limit, depending on each type of equipment manufacturer and each type of company that will that are, have acceptability criteria. But for something like gas turbines, there is the global standards are also there. People have to qualify what is called an FAA, Federal Aviation Agency. There is also the European Aerospace and Space Agency. Then in India, we also have the Directorate General of Civil Aviation. Of course, like ISO, or you need to have regulations and specifications and certifications in order to be able to repair and put a part, just like you have for new make. Except that after a certain amount of repair, after a certain number of operating hours, then the cost of repair, if it exceeds a new make, just like in our home appliances, if we have a microwave oven, for example, and we keep on replacing the magnetron in it, then four times we have replaced it, it outweighs the cost of a new microwave oven, isn't it? So similarly, here we have to look at repair and new make, except the technologies here needed for repair and refurbishment, as I mentioned to you, the alloying additions are so complicated that especially being a process which involves melting and solidification, then the typically these metallic alloys, super alloys, are subjected to solidification cracking, strainage cracking, and liquation cracking. So any technique, including additive manufacturing, is very difficult to overcome all these inherent metallurgical parameters which are inherent in the alloy. In a new make, they are done with very, very great care, in the sense there are very well developed processes like investment casting, typical forging and machining, and so on and so forth. But in a repair, if you have to do that, you're also going to play with the fact that you're having a near net shape part, and that is one of the biggest advantages of additive manufacturing, is you're not having to do much of post processing in terms of conventional machining to build the part to print. So in which case this is a paradox, because A, via additive manufacturing, you're making a near net shape part. But B, if you have to use that to repair an existing part, then what about restoring the material back to its original service standards, acceptance standards in terms of performance until the next interval? So there are a lot of complications. It's quite a complex problem, and that is where we thought, we will take into the advantage of all the advantages given by additive manufacturing. You would have listened to Professor Shikant Joshi speak about it the last 3 days, namely additive offers designed for additive manufacturing in terms of simplification of parts, reduction in terms of the weight via defam, in terms of actually being able to design very, very complex geometries that can improve the performance. Overall, you don't need to stock up parts and lock up liquid cash, and if necessary, we are able to make it perform to much longer standards and much higher in terms of the overall performance in terms of design for the next in line technologies. So we thought, we will take into account the repair and use additive as a unique manufacturing solution. Why? Because of the very high rapid solidification of the order of a lakh to a million degrees per second that takes place in metal additive manufacturing. And we wanted to examine, because necessity is the mother of invention, and almost entirely, if there is no solution available, then we have to look at ingenious ways, and that's where additive comes to the rescue. So I showed you the second slide where the y-axis and the x-axis was going to be like a metric to say which additive technique to choose for which kind of parts or which kind of experimentation you would like to do. So this is just another tabular form of the same, wherein we're looking on the rows where, I have listed all the different types of direct metal laser melting. It is nothing but laser powder bed fusion. Direct metal deposition is nothing but direct energy deposition. And I mentioned to you cold spray is a different powder technique without any melting and solidification, and so on and so forth. But what I would like to highlight mostly is this traffic light kind of qualitative comparison, just to give you an idea of, if you want high precision, then you go to direct metal laser melting or metal additive laser powder bed fusion. If you want to go to great speeds, perhaps this cannot churn out. It's a little bit of a slow process. All are slow, but relatively speaking, the direct energy deposition is much faster as compared to the laser powder bed fusion. If you want to make large footprints, 800 millimeter by 800 millimeter by 1 meter parts, then you're not choosing the right technology. If you go to direct metal laser melting, instead, direct energy deposition is the best, and so on and so forth. I won't run through all of them, but I'm saying, for people who are starting out or who are interested in an application, or even if there is a fundamental studies scientific understanding that we want to do, then it is good to keep in mind which of the techniques is suitable for which application. So these are the metal additive options. So the examples that I'm going to give you are two. This was done in collaboration with Intech DMLS in Bangalore, and the direct energy deposition with DM3D in Michigan. One example I'm going to give you with the laser powder bed fusion, the other is a direct energy deposition. And the first example, these are all the published work done by various students, MTech students, Kaustubh Bhavane during his stint as an intern. Then we've got Santosh and Sudarshan from PSG Tech and from Shastra University. This study on the parameter optimization, both of them were master students again. Then with Sujit, who was from NIT Surathkal, and then once again later when some of this work we were developed in small scale mechanical testing. This is published and done by Sudarshan Reddy. And then Manoj Kumar Chimet was another master student from NIT Surathkal. So the application here is basically a worn part, and most of the structure property correlation I'm showing can be found in all these papers. Um, so the application was a worn out, stage one nozzle vane, which was made of an investment cast cobalt tungsten alloy. And then there was really no repair solution available because this was an investment cast part. And so we came up with the idea of using additive manufacturing using the laser powder bed fusion technique as well as the direct energy deposition technique, just as a proof of concept, to see if we can print this part and then join it by TIG welding. So this is the application. So it's completely like dissimilar material welding, dissimilar manufacturing, and then upon that conventional welding. So it's sort of a hybrid approach in repair, and I'm going to tell you what some of the challenges we faced, and how we overcame that to successfully take it to about a technology readiness level 4 to 5 to 6, all the way from 0 to 1 technology starting point. Okay, so you're all familiar with the layer by layer, welding and solidification process. There's a nice 3D etched microstructure of cobalt chrome moly. This is the build direction. The heat is extracted along this direction in this particular case. And there's a nice etched microstructure that the MTech student Kaustubh Bhavane actually etched, and then he has put together a collage. So what we're talking about in this is what is the first challenges, and I'll keep talking about challenges along the way because now since 2000, in the last 10-15 years, a lot of work has been done by a lot of people all over the world, that to get dense parts is no longer a big, it's not very difficult unless it's a very very high latent heat specimen like aluminum or copper, or some of these metals which reflect the laser light. Their thermal conductivity is so high that you need a much higher power in order to make dense parts. But otherwise, for most other structural popular alloys, getting a dense part is not very difficult. However, what I'm going to try and showcase here is, so this was a small design of experiments we did during the thesis of Santosh from PSG Tech, where we looked at the effect of the layer, energy density, in order to able to get a dense part without any hot isostatic pressing, because most turbine hot section parts, aero engine parts, necessarily need a hipping. Now, sometimes in additive manufacturing, and there are lots of literature as well on Inconel 718 and a few other materials, where people have tried hipping. And the hipping, particularly for additive, because it's very rapid solidification process, sometimes results in segregation of elements. So not always the energy density, that is fine tuned, may be conducive, even if it is a dense part optically. It may or may not give the necessary properties and long term stability. So so this, what we tried was, the first we tried, by changing the laser power, scan speed, layer thickness, and thereby the energy density. As you know, the energy density is nothing but laser power divided by hat spacing into scan speed into layer thickness. And so we also did location specific variation, uh, how the variation in the process parameter is going to have an influence on the microstructure and the mechanical properties of the as built specimen. So when we started with, of course, this was a very bad, long, many, many years ago. So, I mean, it was still the first time. So you see layer lack of fusion, and then you see a lot of inbuilt porosity and sometimes unmelted particles, if you can see this. So soon after, with the energy density I showed you in the previous slide, we were able to get a very dense structure, one with hipping and one without even hipping. So this was quite an achievement those days, because without hipping, first of all, there is a process step that is reduced. Secondly, if you're able to avoid a process step, time is also less. And lastly, if without hipping is going to give you even better properties and long term thermal stability, then why not? It is a win-win. So as we moved on to this, we went on to look at the which of these parameter optimization. In some sense, as I showed you two slides earlier, what is the hat spacing, which tells you the overlap in the layers, as you might have learned earlier this week. And we are also looking at what kind of, is it a checker, is it chessboard, or is it a zigzag contour, and so on and so forth. So this whole thing was optimized so that the productivity is also met with, and it's not a very, very slow process. At the same time, there is no compromise on the y equal to f of x, in this case is density and simple room temperature mechanical properties. But the application itself needed high temperature properties. I told you it was a hot section part, isn't it? So what we went on to do is, we took the microstructure of the as-built structure. I showed you these. Did some optical microscopy and very detailed scanning electron microscopy, as well as very detailed transmission electron microscopy, to make sure that we understood what was the phase and what was the any metastable phases, or so that the what can I say, the equilibrium stability could be mapped thoroughly from the as built structure. However, in principle, we had to heat treat the samples, because remember, we were going to do a weld repair, so which means you need to do a pre weld and a post weld heat treatment. So as part of the master's thesis, Kaustubh tried a bunch of heat treatments, and the heat treatment resulted in a microstructure which ended up with a beautiful uniform recrystallized microstructure. You can see some very fine grains out here. This is blown up out here in the lower pictures. And the second or third challenge that trying to highlight here is the fact that typically in these kind of where the heat transfer is takes plays a major role, then you kind of have to watch out for not always having a equiax structure without any texture, without any orientation effect. So luckily in our case, you can see this is an electron backscatter diffraction image, EBSD pattern, and it shows that this fine grain microstructure, recrystallized microstructure, after heat treating the cobalt chromoly, is actually not having any preferred texture. So that was a great thing. So with that, we went on to go into the next part of it, which is to evaluate in detail the mechanical properties, and then details of which um, you can look it up in the paper. But what I want, since this is also the subject is also to look at successful qualifications, one of the things you need to look out for is the surface roughness in any surface optimization or surface roughness in any near net shape part via additive manufacturing. I did mention to you earlier there's a direct energy deposition. The surface roughness is quite rough because it's a high throughput rate, larger powder particle sizes, and a much faster way of building the part, which needs or necessitates further machining to the near net shape geometry. Whereas in the laser powder bed fusion, whose example I'm showing you right now, you can do a little bit of the process optimization using the laser parameters itself, the energy density, variability, so that you are able to minimize the surface roughness, not only on the surface, what is showing in condition A versus condition B, but also inside any geometrical features, such as a hole. So you can see that between condition A and condition B, the surface roughness has been reduced from nearly 20 to less than 5 micrometers Ra. Whereas in the coal also, the rough features were very rough, very sharp corners, unmelted particles you can see on the left hand side. And on the right hand side, it's much, much reduced. So one of the challenges is to work through the parameter optimization, because if even if an external surface is there, you can machine it out. However, if you're having an internal surface, first of all, inspection is very difficult. The previous speakers in the course might have highlighted those as one of the big challenges. Yes, it is a challenge because we can't cut up every single part. Even if we cut it up, how do we know the cut up portion is the location where we are having these roughnesses? So one of the things to do is to develop intelligent gauges which can actually ensure that you're able to uh, physically measure the surface roughness of the built part, and especially in geometry such as cooling holes, and then pair it up with numerical calculations and flow physics calculations to make sure there are no hot spot or there's no constriction of the cooling hole, leading to less air passing through it, and so on and so forth. So heat transfer, that's what we did. Now, when we move on further to actually scale up and say we are successful with the microstructure, we're successful without any texture, we are successful in the mechanical properties and the surface roughness, then the next thing would be to do from an experimental coupon level to a larger scale, obviously, in the build plate. And this is where there is another big challenge to watch out for in the qualification. As you increase the number of parts in the build plate, then you can have distortion because of the heat transfer that is different when you're when you're making one or two parts to making 20 or 30 in the build plate. So what happened in this case as well is because of residual stresses and the heat transfer to print scaling up the number of parts, we also face that. So that's what I'm showing in the left hand side picture with the red colored circle. So we measured the residual stress experimentally through sine square psi technique using X-ray diffraction, and we also did some numerical calculations to then overcome this, and then we incorporated a small design for additive manufacturing, such as these green colored struts here, so that when we are increasing the number of parts, then we cut up in order to remove the part from the build plate, we build these struts so that you can only cut these struts out. Okay, so experimentally determine the residual stress along and perpendicular to the build direction through X-ray diffraction. Then establish correlation of residual stress in the coupon for with necessary build parameter optimization. Then perform the transient thermomechanical fatigue finite element analysis, numerical modeling, and then correlate the residual stress of the experimental measurements in the numerical simulations, and in such a way that optimize the parameters. So that is the recipe highlighted in these four boxes. So with that, that is what we did, and this is Again, this part of the this page is published by Manoj Kumar Chimet's work. So what we did is we determined X-ray in with X-ray diffraction from the surface through thickness, then as a function of as printed condition grid blasted and the heat treatment 950 degrees, and as a function of heat treatment, we were able to see whether initially it is tensile stress. You can see this is the zero axis on the surface. There is a tensile stress. Then when you grid blast it, it becomes compressive residual stress, minus 300 megapascal. Then when you heat treat it to 950 degrees, this is the microstructure of this, which is again a little bit of tensile. And when I cool it, I mean, when I heat treat it to 1150 degrees and cool it, for this equax structure, it has a maximum compressive residual stress. So this is all through thickness measurement. So having established that, and with a grasp of the complete structure property correlations, including scalability. So these are some pictures taken in the manufacturing place in Intech TMLS. You can see we built a qualification package. This is the support structure. These are the test coupons for microstructure and mechanical property determination. Then, as I told you, we incorporated at least 5 to 6 challenges in terms of how did we take it from the coupon level all the way to the scalability and qualification. Okay. So, design for additive manufacturing. Then we took on further fundamental studies. This is also part of Kaustub's Bhavane's work. So we took this and we uh, developed a technique to build this additively manufactured coupon on the repaired part, which is the vein. And very happy that the failure did not take place exactly at the joint. So the failure was actually very much inside the cast FSX414, as you can see here. This is the distance about 6 millimeter also. This is the distance where the safe zone is the additively manufactured coupon zone of cobalt chromoly. But one of the things I wanted to share here is the big challenge again. Because it was a thin part that was welded, there are no well defined test techniques to qualify this particular joint, because typical test samples are quite bulky, as shown here in this example. So this is ASTM M6, and this is one of the smallest specimens. Obviously, I can't take it out of such a thin joint where I've joined it by a weld repair. So there is a big need for developing small scale testing and getting it qualified in order to accelerate the applications of using additive manufacturing for both new make, advanced designs and for repair solutions. So, I will leave you with this thought and move on to the you know next example. This is what we the top part is what we completed and I shared with you, and these are the welded parts. What we also did, shared with you right at the beginning for the same example, is we tried in parallel using direct energy deposition and directly coating on this, adjust the fixture and so on, that you directly cut the damaged part and build the damaged part, build it using direct energy deposition. With that also we had success story. It was not bad at all. Again, this is part of Kaustub's work, published in his MTech thesis. What you could see here, the microstructure is this is the cast FSX414, and this is the additively powder based direct energy deposition. Except that here, as compared to the laser powder bed fusion, the columns are much larger, and there is a columnar or a epitaxial growth, unlike in the laser powder bed fusion, where we said there was no texture at all. And you can see the primary dendrite arm spacing, the secondary, dendritic arm spacing. You can see small dendritic features emanating out of the primary arms. So this has a very directional structure and quite different to that of the laser powder bed fusion. Of course, the material here is directly, the material of construction of the vein that that is used for the example in this particular case study. So now with these two examples, I'm going to move a little bit into showing an example again published in Proceedings of the ASME Gas Turbine India. This was done During this stint, colleagues Hariharan and others were working on this, wherein we wanted to well repair this particular part, and again partnered with DM3D in Michigan. And this was a combustion swirler, which is responsible for NOx reduction. And there was worn out teeth out here, and this could not be repaired. They were all thrown out and scrapped. So we came up with a solution of using direct energy deposition. We started by measuring the, from the throw worn out tubes, the long meter long tubes made out of stainless steel. We calculated the maximum extent of wear from a few samples, maybe 15 to 20 of those tubes. The total system wear was calculated using a digital microscope and optical microscope. And then we found a solution to use direct energy deposition to deposit different materials which were much harder, because otherwise there's no repair solution. They were throwing all these parts away into the scrap. And then these were experiments. The design of experiments was done by a student, an intern at DM3D, and they developed the process parameters, and in about 5 to 6 months came up with a perfect solution for this geometry, where they had to deposit a much harder lubricious metal, because it is going to undergo wear again when the combustion, when they put it back into the gas turbine. So they had to find this the extent of this new fingering that you can see outside here. Had to find the extent of maximum wear and compare it with the case where there was no solution available. So then what, these were tests done in the lab, wherein we used a fretting fatigue of this geometry. You can see the coating is about, the whole thing is about 2 millimeters L605 on the substrate. And we looked at the cross section, of both the shoe and the block, and see if there is a correlation between the two in terms of what is going to be the wear by additively manufacturing and adding a lubricious wear resistant layer on top of the on top of the Greek ascalon or the stainless steel. So once we established this, then did a lot of dilution of the interface. I think it's here. So we did a lot of microstructural studies as well, and then looked to see that there was no cause for concern. And then using the wear testing experiment, in this particular case, we didn't have to do anything other than the wear testing. Of course, hardness was done as a precaution, but the actual design was one of wear. So we actually simulated the wear conditions, and this was qualified in 2017, as you can see here. 16. So it took about 8 months to get all these correct parameters and qualify these um, repairs in the repair shop. Okay. Okay, so the last example is that of cold spray, because the cold spray is basically not a melting and solidification process. Here, what happens is you have a nozzle, which is a convergent divergent nozzle, using process gas such as very low atomic number and weight gases like helium and nitrogen. The gases carry these powder particles similar in size range to that of the laser powder bed fusion process, which is between 5 to about 30 to 40 micrometers. And it gushes it creates a sort of a Venturi effect, and the gas carries with a momentum and goes and smashes the particles onto the substrate that it is going to have an effect on. And the severe plastic deformation, there's no melting or solidification, is used for a number of components, for repair, for corrosion, for wear, for very difficult to weld materials, and so on and so forth. So these are all the references from which we've taken. A couple of master students, Vignesh Chandrasekhar, who worked on it, and there were colleagues. There were also colleagues whose names are listed here who contributed to this extensively. And then we also partnered with university, Indian Institute of Science, for Satyam Suvas and Chandan Srivastava, and so on. So I'd like to, all the work presented is from some of these papers here. So Then, as I mentioned to you, it's a convergent diverging nozzle. Powder particles go and form a coated layer on the substrate that you can see here, without having any of the ill effects of conventional thermal spray process in terms of poor deposition efficiency, and not very effective for restoration of components, because there's so many advantages. Basically, it is relatively cold spray, and you can even make coatings, or you can make material as thick as even 25 millimeters, 20 millimeters, 15 millimeters. All it has to do is it has to be a metal which is undergoing plastic deformation in order to be able to spray on this. And the other advantage, especially the lot of Air Force related applications in the last 15 years, where they're using cold spray for very difficult to weld and repair alloys, like light alloys like magnesium, titanium, which will catch fire, aero engine materials, aluminum, very very difficult to repair, cast iron, for example. So all these, cold spray is seen as a very good repair technique. Moreover, cold spray is also akin to short peening, so that fine powder particles are coming and impinging on it. Since some of the low light elements like aluminum, titanium, it even is able to give some kind of a compressive residual stress and enhances the fatigue behavior of the base metal. So a lot of advantage with cold spray. Basically, in this case, our collaborator was ASP Industries in Akron, Ohio, and so we start with powder particles. You can see a distribution of particle size. It almost like a bimodal here in this particular picture. Some of them are just about 5 microns, some of them are 30 microns. And so we ourselves in the lab, um, you know, were able to make this onto a lower lye steel substrate, and spray up to 3 to 5 millimeter thick coating without the coatings falling off. And we tried a comparison between helium and nitrogen as a process gas. And for the sake of the application that we were considering, the substrate materials were chrome olivine and Inconel 718. So, and the coating thicknesses we played around between zero point 0.5 to 3 micron RA. I'm sorry, 3 millimeters. And of course, the micron RA is a surface roughness. So typically, this is how the microstructures look. This is the substrate and this is the coating. Likewise, this is the substrate and this is the coating. I think in the top picture, you can't really see the substrates. So we are trying two different nickel-based alloys for better functional properties such as better corrosion response and better wear resistance onto chrome olivine steel. Okay, so you can see within the compared, this particular slide comparison of the microstructure, you can see that the cold spray coating is fairly dense, especially the one sprayed using helium as a process gas. The nitrogen does give some porosity, but it's really not such a big cause for concern. And you can see that these coatings are so hard, nearly 500 to 550 HV in hardness, for both Inconel 718 and Inconel 625. Then we went on to do, after the microstructure, the statutory bond adhesions test. This is as per ASTM C633 standard, which simply implies that when you have a coated round specimen, then you apply some specific glue to it, and then you pull it in uniaxial tension, and you see what is the nature of the failure. Is it cohesive? It is adhesive, or is it glue failure? Fortunately, if it is glue failure, then it at least tells you, if the glue to glue strength is about 100 megapascal, it at least tells you that your coating adhesion strength is more than 100 megapascal. So that is why it's a very very crude and qualitative test, but it's a very engineering ballpark test, so that we're able to compare different uh, materials and different processing techniques. So that is what is shown here. In blue is all the Inconel 718 on the chrome olivine, and in the red color is Inconel 625 on 4130. You can see here that the nitrogen gas, the porosity that we saw in the previous slide, using nitrogen as a process gas, there may be some problems with respect to the bonding between the coating and the substrate. But that can be overcome by doing heat treatments and giving a metallurgical bonding. Then this is just an example of one other mechanical property and a challenge that we faced. Namely, if I make a 3 millimeter coating also on a substrate, there are no test techniques available to test such thick coat, thick um, coated substrates. Normally, we make a thin coating and we assume that the substrate is infinite thickness. Whereas all I'm trying to highlight in this slide is the green colored symbols are with nitrogen, the red is with helium. And basically, at this A ratio, we had to tone down the coating thickness so much that it is seen as a thin film on the steel substrate. And the black line is the baseline number of fatigue cycles to failure. Um, uh, the black line is the baseline for the chromoly steel. So again, this is another big challenge, and it is necessary to again develop test techniques that are commensurate with the near net shape additive manufacturing, as I had already also indicated during the laser powder bed fusion, the hybrid manufacturing process. So, and then one of the things, another challenge that I wanted to show you in this, even though the left hand curve shows the residual stresses of the through thickness of the coating of Inconel 718 on chromoly, right? But one of the challenges we face is also the fact that in very heavy high density structural materials like nickel, cobalt, and all. Sometimes a cold spray process, while it works really well for lighter alloys and metals, sometimes it can completely recrystallize some severe plastic deformation into the steel substrate, so much so that the substrate um, can alter the microstructure or the texture, and it can lead to premature failure despite having the compressive stresses. So in this case, you can see recrystallized grains. This is the coating substrate interface. This is the coating. This is the substrate. And you can see a large gradation in the microstructure. And at the vicinity of the interface where the severe plastic deformation has taken place, you can see completely recrystallized microstructure out here. Okay, so with that, what we did is we took all these. This is for drilling and production subsea oil and gas systems. We applied the cold spray solution in the lab scale, transfer the technology to ASB Industries, and this is the machined uh, after machining. Okay, so now I just wanted to. I hope I gave you a glimpse. We could have gone into details of each and every one of them, but since I've only taken snippets from open domain published work from those journals that I shared with you. What is it that we do for accelerated qualifications and certifications? I just wanted to show you that a number of organizations are there, which are specializing in creating specifications, powder based specifications for each and every one of the additive manufacturing chemistries, as well as techniques of additive manufacturing. And of course, we are looking at accelerated part qualifications in terms of repeatability and reproducibility. Then we do need to keep in mind a whole bunch of both operations as well as metallurgical challenges. Some of those examples I showed you: surface roughness, heat treatment optimization, and then isotropy of microstructure and texture, and then long-term stability, and then isotropy of mechanical properties at that particular temperature, and how the surface roughness can be tailored to optimize the design for additive manufacturing, and so on and so forth. So of course, inspection technologies is a big area that the whole additive community could do with some novelty and state of the art techniques. Based on my own experience of what are the different challenges in AM qualification. If you're interested, you can have a look at that. And whatever I showed was in terms of density, residual stress, mechanical properties, and well, I think that's all I had time for. So what I wanted to show you in the last slide is, in order to go into newer and newer material compositions, such as IN 939, such as new aluminum alloys, high strength aluminum alloys, copper alloys, niobium alloys, cobalt alloys, whatever be it, moving into newer alloys is, fraught with the lessons learned from the challenges faced in the previous qualifications. So, so during I did actually did a lot of work on developing new hybrid alloys, small scale mechanical testing, all these during my stint with Pratt and Whitney in the more recent 5 years. And if there are any published work, I request you to have a look at it, especially in terms of a new technique of small scale testing of bending creep. We have published at least 4 papers on that in the recent 2 to 3 years, and that will give you an idea of the direction forward in qualification of additive parts for various applications. So I would like to acknowledge a whole bunch of people, professors from ISC, IIT Bombay, IIT Hyderabad, IIT Roper, and several postdoctoral and senior PhD students, as well as all the MTech students who, and of course, the teams that gave me an opportunity to work all through so many years on, very brand new technology of additive and how to enable qualification of additive parts in an accelerated time frame. So with that, I'm going to uh, end this presentation and be very happy to answer any questions. And of course, with a big acknowledgement to all the organizations that I work for, and all the collaborations. The key in all these, I mentioned to you, each of those papers were part of an MTech thesis. So, really, the MTech interns who came and worked it and enabled publishing some little bit at least, certainly all the universities, IISc, IIT Madras, IIT Hyderabad, IIT Roper, NIT Surathkal, NIT Trichy, Shastra University, PSD Tech, and so on and so forth. And then the people who helped us, as sort of a supply chain for the additive parts as well as the cold spray parts. And then thank you very much for your attention, and I'll be happy to ask questions. Thank you. Um, I have finished, Dr. Manjaya.